Here's a number I want you to sit with for a second. Not just read and move past it like it's another headline statistic. But actually picture it in your mind the way a physicist is forced to when the numbers stop behaving like ordinary experience. 5,000 degrees Fahrenheit, that is roughly the temperature the Orion capsule will generate on its surface when it slams back into Earth's atmosphere at about 25,000 miles per hour. And if that doesn't immediately bother you, it probably means you haven't translated it into something your intuition can grab onto yet. Because what that really means is that for a brief stretch of time, a thin layer of air around that spacecraft will be heated to something not too far off from stellar condition. And inside that structure are 4 people who are relying on a carefully engineered process of controlled destruction to keep them alive. Now, you might be tempted to think the dangerous part of this mission was going out there, going all the way to the moon, looping around it, being farther from Earth than anyone has been in over half a century. But that instinct is exactly backwards in a very interesting way, because getting there is mostly about vacuum. And vacuum, for all its hostility to human biology, is actually a relatively quiet physical environment. Nothing is pushing on you. Nothing is trying to rip energy out of your motion except the slow pull of gravity. But coming back, that's where the universe suddenly becomes aggressive again. Because now you're taking all that velocity you built up and asking the atmosphere to deal with it. Let me try to put that in a way that doesn't sound abstract. Because I remember the first time I really understood what heating from compression meant. It wasn't from a textbook. It was from pushing my hand quickly through water and noticing that the faster I went, the more resistance I felt, and then realizing that if you keep increasing that speed far enough, the medium doesn't have time to move out of the way anymore. It just piles up in front of you. And when you compress a gas like that, you don't get a gentle increase in temperature. You get a violent one, the kind that turns air into plasma. And plasma doesn't behave like the air you're used to breathing. It glows. It conducts electricity. It wraps the spacecraft in something closer to a miniature star than anything we encounter in daily life. So when I say 5,000 degrees, I'm not trying to impress you with a big number. I'm trying to get you to notice a very specific physical fact, which is that the Orion capsule is not resisting heat in the way a heat shield on a car engine might. It is managing a process where the outer material literally burns away in a controlled fashion, carrying energy with it as it erodes. And that means the safety of the crew depends not on something staying intact, but on something being consumed at exactly the right rate, not too fast, not too slow, not unevenly, not unpredictably. And here's where it starts to get a little uncomfortable if you follow the logic all the way through, instead of stopping at the reassuring words, because you might hear that NASA has tested this, that similar systems have worked before, that we've been to the moon and back. And all of that is true in a broad historical sense, but the details are where physics lives. And the details here are different enough that you don't get to simply borrow confidence from the past without checking whether the assumptions still line up. The Orion capsule is coming in faster than typical low Earth orbit returns. It's using a different re-entry profile than the old Apollo missions. And perhaps most importantly, the last time this exact vehicle went through this process, there were things about how its heat shield behaved that didn't match what the model said should happen. Not catastrophic things, not failures, but deviations. And in physics, a deviation is not something you wave away. It's something you stare at, because it's reality telling you that your description of the system is incomplete. Now imagine, not in a dramatic way, but in a very quiet, technical way, that you are one of the people sitting inside that capsule, strapped in, knowing that in a short amount of time you are going to hit an invisible boundary where the rules change from orbital mechanics. which is almost peaceful in its predictability, to high-energy fluid dynamics, which is anything but. And there is a layer of material between you and that plasma that has to behave exactly the way it's supposed to, based on models that have already shown they're not perfect. I'm not saying that to suggest something will go wrong, because physics doesn't deal in that kind of narrative certainty. What I'm saying is that the most important part of this mission is not the part where you see the moon in the window. It's the part where you don't see anything clearly at all, because the outside of your spacecraft has turned into a bright, ionized blur, and every calculation that was made on the ground is being checked against reality in real time. And if you're really paying attention, you start to realize that coming home in this context is not a passive thing. It's not a guarantee built into the mission. Once you've gone far enough, it's an active, delicate negotiation with physics itself, one that only works if every assumption you made about how matter, energy, and motion behave under extreme conditions is close enough to the truth to keep 4 human beings from finding out exactly where it isn't. If you were watching this mission from the outside, the moment that probably felt like the climax was the flyby itself, that clean arc around the moon, the photographs, the distance, the sense that human beings had once again reached out to something that sits nearly 400,000 kilometers away and then turned back. And I understand why that's the moment people hold on to, because it's visible, it's symbolic, it's easy to recognize as an achievement, but if you sit a little closer to the physics of what's actually happening, you start to notice something quieter and, in a way, more interesting, which is that the real story doesn't peak at the moon. It flattens out and then shifts direction. Right after the flyby, nothing dramatic happens in the way people expect drama to look. There's no sudden burst of activity, no visible turning point, just a spacecraft already moving at enormous speed, now subtly redirected by the moon's gravity into what's called a free return trajectory. And that phrase sounds almost poetic, like something gentle and forgiving, as if the solar system is offering you a path home, but it's really just geometry doing its job. You pass close enough to the moon at the right angle, and its gravitational field bends your path so that, without firing engines, you fall back toward Earth along a curve that was set up days earlier. I remember the first time I understood this kind of motion properly, not from equations, but from thinking about throwing a ball sideways while it's falling and realizing that if you throw it fast enough, it doesn't hit the ground where you expect, it curves. And if you could throw it fast enough and the Earth were smooth enough, it would keep missing the ground entirely, orbiting. And this is the same idea extended out into space, except now the ground you're missing and curving around is not just Earth, but the combined geometry of Earth and Moon together. And the trajectory you're on is less like steering a car and more like having already committed to a path that only looks flexible because it's so large. And this is the part that doesn't make it into the headlines, because it doesn't look like anything is happening. But inside mission control and inside the capsule, everything has changed in tone. The mission is no longer about going somewhere. It's about coming back correctly. And that distinction matters more than it sounds, because going somewhere allows for adjustment, for correction, for a certain amount of improvisation, but coming back, especially along a free return path, is about verifying that what you set in motion earlier is still aligned with what you need now. If you could listen in on the communications at this stage, you wouldn't hear celebration. You'd hear something more procedural, more measured, a rhythm of checklists and confirmations, because once the trajectory is established, the job shifts from exploration to validation. Every system that will matter during re-entry is being checked, not in a dramatic way, but in a repetitive, almost monotonous sequence. And that monotony is exactly what keeps people alive in high-risk environments, because it replaces guesswork with structure. The crew themselves are no longer tourists of deep space. If they ever were, they are configuring the vehicle, thinking ahead to a phase of the mission where they will have less control, not more. And there's something about that transition that I find more revealing than any photograph of the moon, because it shows you where the real dependency lies, not on human reaction time, not on last-minute decisions, but on systems that have to work the way they were designed to work when the environment becomes too fast, too hot, too unforgiving for improvisation. You might think of this as the quiet part of the mission, but that's only because nothing is visibly failing. Nothing is visibly changing, and I've learned to be a little suspicious of situations like that, because in physics, the absence of visible change doesn't mean nothing is happening. It often means that the important variables are evolving in ways that aren't directly observable. The trajectory tightening toward an entry corridor, the spacecraft's orientation being adjusted, the timing of future maneuvers being locked in, all of it moving toward a point where options begin to narrow. There's a subtle shift here that's easy to miss if you're not looking for it. And once you see it, you can't really unsee it, which is that earlier in the mission, the crew had multiple layers of redundancy, multiple ways to adjust, to delay, to reconsider. But as they move along this return path, the geometry itself starts to remove those degrees of freedom, not abruptly, but steadily, until you reach a point where the path you're on is the path you're going to follow. And the question is no longer, what do we want to do next, but have we already set things up correctly for what's about to happen? I've always found it a little unsettling how much of space flight works like that. Decisions made far in advance unfolding later in conditions where changing them is no longer practical. And if you put yourself, even briefly, in that capsule, looking out at a planet that is slowly getting larger, knowing that the most demanding part of your journey hasn't happened yet, and that it will depend heavily on things that were decided before you ever saw the moon up close, you start to get a different sense of what this mission really is. Because at this point, the spacecraft is not heading toward a destination in the way we usually imagine. It is converging on a very specific set of conditions, a narrow slice of space and angle and timing where the physics of re-entry will either align with the design or expose the places where it doesn't. And everything that looked like the main event a few hours ago quietly recedes behind that fact. If you take everything we've talked about so far and you compress it into a single moment where the physics becomes impossible to ignore, it's this phase right here, the one people casually call re-entry, as if it were a single event, when in reality, for this vehicle, it is a sequence, a negotiation, almost a conversation between the spacecraft and the atmosphere. And what makes it particularly interesting is that Orion is not coming straight down the way the older capsules did. It's doing something that sounds deceptively simple until you try to think through what it actually requires. It is going to hit the atmosphere, generate lift, and then leave it again before coming back in for a second pass. Now, the first time you hear that, it almost sounds like a trick, like skipping a stone across water. And that's not a terrible analogy, except you have to remember that the water in this case is air being compressed to plasma temperatures, and the stone is carrying 4 human beings inside it. And the margin for getting the angle wrong is not something you can casually adjust once you've committed, because at these speeds, small differences don't stay small for very long. I used to think of re-entry as a kind of brute force process. You come in fast. The atmosphere slows you down. You endure the heating, and eventually you're safe. But once you look at skip re-entry more carefully, you realize it's much closer to flying than falling. The capsule is actually generating aerodynamic lift. Not a lot compared to an airplane, but enough that by adjusting its orientation, it can change how deeply it penetrates the atmosphere during that first pass. And that means the guidance system is not just writing physics. It is actively shaping the trajectory in real time. And this is where I want you to pause for a second and picture what that really implies. Because during this phase, the spacecraft is surrounded by plasma, a layer of ionized gas so hot and dense that it starts to behave electrically. And one of the consequences of that, which people mention, but don't usually dwell on, is that radio signals don't pass through it. They're absorbed, scattered, effectively blocked. And what that means in practice is that at the exact moment when the spacecraft is experiencing its most extreme environment, it also becomes silent. There is a point, a very real one, where mission control stops hearing from the capsule. The data drops out. The voice loop goes quiet. And everything on the ground reduces to waiting. Not because nobody cares, but because there is nothing they can do. No command can be sent. No corrections can be uploaded. And for those few minutes, the spacecraft is entirely on its own, navigating a situation that is changing faster than any human could respond to, even if communication were still possible. I remember once taking apart a piece of electronics, a simple one, just to see how it worked, and noticing that as long as each component behaved within its expected range, the whole system did exactly what it was supposed to do. But the moment one signal drifted just a little outside that range, not even a failure, just a deviation, the behavior of the entire circuit changed in ways that weren't obvious from looking at any single part, and that stuck with me because it's a small-scale version of what's happening here. Except now the circuit is a spacecraft moving at hypersonic speed through a rapidly changing fluid environment. During that first atmospheric pass, the capsule dips into the upper layers, builds up heat, experiences deceleration, and then, if everything is working correctly, it generates enough lift to climb back out again. Not into space in the usual sense, but high enough that the heating drops, the plasma dissipates, and communication briefly returns. And in that window, engineers on the ground get a snapshot of what just happened. They see the data, the temperatures, the trajectory, and they confirm that the vehicle is still within the expected envelope. But here's the subtle part that I don't think gets enough attention. The second entry is not starting from a clean slate. It is starting from whatever the first pass produced. Whatever the heat shield actually did, whatever tiny changes occurred in the vehicle's surface, whatever the guidance system corrected for, all of that feeds directly into the conditions of the second descent. And now the system has to do it again. Another heating peak, another plasma sheath, another blackout. So when people describe skip re-entry as a way to make things easier on the crew by spreading out the deceleration, that's true in one very specific sense. The peak forces are lower. But what you've traded for, that is a process that depends more heavily on continuous precise control and on systems that must behave correctly, not once, but twice, under conditions where feedback from the ground disappears exactly when you would most want it. And if you're sitting inside that capsule, you don't experience any of this as a diagram or a set of equations. You feel the forces build. You see the glow outside the window, and then, without any announcement, the connection to everyone else simply ends, not because something has gone wrong, but because the physics of the situation doesn't allow it to continue. And for a few minutes, the entire outcome of the mission rests on a machine executing a sequence of decisions faster than you can follow, and in an environment you cannot directly perceive. It's a very strange kind of trust. Not the kind where you believe nothing will fail, but the kind where you accept that if something does, you won't be part of the conversation about it until after the fact. And the system you're inside will either carry you through that silence or it won't. And there is no intermediate state where you get to reach out and adjust the outcome. Before there were 4 people sitting inside this vehicle, trusting it to bring them home, there was a version of the same spacecraft that made the journey alone. No crew, no life support concerns, no human risk, just a full system test designed to answer a very straightforward question. Does the hardware behave the way we think it does when it goes out there and comes back through that wall of plasma we've been talking about? And from a distance, the answer looked like a clean yes. The mission completed. The capsule splashed down. The images were good. The headlines were positive. And if you stopped there, you would walk away with the impression that the system had been validated in exactly the way it was supposed to be. But engineers don't stop there. And this is one of those moments where the difference between how something looks publicly and how it feels technically becomes very sharp. Because once that capsule was recovered and brought back, people started looking at the heat shield not as a symbol of success, but as a physical record of what actually happened during re-entry. And that's where the story becomes more interesting. Not because something failed, but because something didn't quite line up. The material on that heat shield is called avcoat. And the idea behind it is not to keep heat out in the way you might first imagine, but to manage it by sacrificing itself in a very controlled way. The outer layer chars, and all this carries energy away as it breaks down. And if everything works perfectly, it does so evenly enough that the underlying structure never experiences temperatures beyond what it can handle. It's a design with heritage going back to earlier missions. And on paper, the physics is well understood. You can model how the material should ablate under certain heating conditions. You can predict how much mass will be lost, how the surface will change, how the thermal load will be distributed. Now, here's the part where reality starts to push back a little, because when they examined the Artemis, one heat shield, they found that the charring pattern was not as uniform as the models had predicted. There were regions where the material had eroded more deeply than expected, and not in a random, chaotic way, but in patterns that suggested something systematic in the actual flight environment wasn't being fully captured by the simulations. And I want to be careful here, because it's easy to hear that and jump straight to failure. But that's not what happened. The shield did its job. The capsule was protected. There was no structural breach, no immediate danger to anything inside. What you have instead is something that, from a physics perspective, is both more subtle and more important, which is a divergence between prediction and observation. And if you've ever worked through a problem where your calculation gives you one answer and the experiment gives you another, you know that feeling. It's not panic. It's not relief either. It's a kind of tension, because you now know that your understanding is incomplete, even if the outcome happened to fall within acceptable limits. NASA went through the process you would expect. They analyzed the data, updated the models, incorporated the observed behavior into their simulations, and reassessed whether the system still met the criteria for a crewed mission. And the conclusion was that it did, that the margins were still sufficient, that the risk remained within what they define as acceptable. And that phrase, acceptable risk, is one of those terms that sounds reassuring until you look at what it actually means, because it does not mean fully understood. It means bounded well enough that we are willing to proceed. I remember once working through a calculation where everything seemed consistent until I changed one assumption, And suddenly the entire result shifted in a way I hadn't anticipated. And the unsettling part wasn't that the system behaved differently. It was that I hadn't realized how sensitive it was to that assumption in the first place. And that's the kind of thing you start thinking about when you hear that a model has been updated to match data rather than derived from a complete understanding of the underlying mechanism, because a model that explains what already happened is not automatically a model that will predict what happens next, especially when the next situation is not identical to the previous one. And this is where Artemis two steps into a slightly different regime. The flight duration is longer. The thermal history of the vehicle is different. The mass distribution changes when you have a crew on board. And the reentry profile involves that two-phase skip we talked about earlier, which means the heat shield is going to experience a sequence of conditions rather than a single, simpler event. So when you think about that layer of material between the plasma and the people inside, you're not just thinking about whether it can survive. You're thinking about how precisely its behavior matches the assumptions built into the guidance system. The thermal models the entire chain of calculations that define how the spacecraft moves and how it dissipates energy. And the last time this exact system went through that process, it behaved in ways that were close enough to be safe, but different enough to force a revision. And there's something about that distinction that tends to get smoothed over in public discussions because it doesn't fit neatly into a success or failure category. But from where I'm sitting, that's exactly where the interesting physics is. Not in the cases where everything lines up perfectly, but in the ones where it almost does. Because almost is where you learn how much of your understanding is actually grounded in reality and how much of it is still leaning on assumptions that haven't been fully tested yet. While all of this is unfolding, while the trajectory is tightening and the heat shield is waiting for its turn to be tested against reality, there is something else happening that doesn't sit neatly inside the spacecraft. Something that doesn't care about mission timelines or carefully constructed entry corridors. And that is the environment they've been flying through for the past 3 days. Because once you leave low Earth orbit, you are no longer inside the comfortable shielding of the planet's magnetic field. You are out in a region where the sun has a much more direct say in what happens to you. And the sun is not a quiet object. Now, when people hear space weather, they often imagine something dramatic. Flares, explosion, bright bursts of energy. But most of what matters for a mission like this is not dramatic at all. It's quiet, persistent, almost invisible. And that's exactly why it's easy to underestimate. Because instead of a single violent event, what you have is a sustained environment of high-energy particles, especially electrons, moving through space and interacting with anything they encounter, including the spacecraft that is carrying those 4 people back home. If you look at the numbers, you see elevated electron flux levels over the entire transit, not something that spikes and disappears, but something that stays high for long enough to matter. And what those electrons do is not immediately obvious in the way heat or force is. They don't slam into the spacecraft and announce themselves. They seep in, they penetrate outer layers, and they embed themselves in materials that, under normal conditions, you would think of as electrically quiet. Plastics, composite, insulation, the kinds of materials that are everywhere inside a modern spacecraft. I remember the first time I learned that insulating materials could actually store charge internally, not just on their surface. It felt counterintuitive because we're used to thinking of insulators as passive, as barriers, but in the presence of high-energy electrons, they become something else entirely. They start to accumulate charge within their structure, and because they don't conduct well, that charge doesn't immediately flow away. It stays there, building slowly, invisibly, until at some point it has to go somewhere. This is what engineers call dielectric charging. And the name sounds technical enough that you might be tempted to file it away as one of those niche concerns that experts worry about. But that doesn't really affect the big picture. Except here, the big picture is built out of thousands of small electrical signals, senses feeding data into guidance systems, timing circuits, coordinating operations, digital systems interpreting inputs and deciding how to respond. And all of those depend on signals being just slightly more stable than the noise around them. So imagine what it means to have a spacecraft that has spent 72 hours in an environment where electrons have been quietly accumulating inside its materials, not enough to cause immediate failure, not enough to trigger alarms, but enough that the probability of small, unpredictable discharge events is no longer negligible. And when those discharges happen, they don't announce themselves as catastrophic breakdowns. They show up as something much more subtle. A transient spike in a sensor, a momentary glitch in a data stream, a timing irregularity that lasts just long enough to be recorded but not long enough to be obvious. And on its own, that kind of thing is not a crisis. Modern systems are designed to tolerate noise, to filter it out, to rely on redundancy. But you have to think about when this is happening, not just what is happening, because the spacecraft is not going to spend the rest of its journey in a calm, forgiving environment. It is heading into a phase where the guidance system will be making continuous, precise adjustments based on sensor inputs, where small deviations can propagate through the system in ways that are not always linear. At the same time, you have the sun itself, not in a catastrophic state, but not entirely quiet either, with an active region that carries a non-zero probability of producing a high-energy flare. And I want you to think carefully about what a 10% probability means in this context. Because in everyday life, 10% feels small, something you might ignore. But when you're dealing with a system where there is no abort option, where you cannot step away and try again later, that number doesn't just sit there abstractly. It becomes part of the background uncertainty you carry into the most critical phase of the mission. There's a tendency to separate these things in our minds, to think of the heat shield as one problem, the guidance system as another, space weather as something else entirely. But in reality, they're all part of the same system, interacting, overlapping, influencing each other in ways that are not always obvious from looking at any one piece in isolation. And what you have at this point in the mission is a spacecraft that has been quietly altered, not dramatically, not visibly, but measurably by the environment it has passed through. And if you're sitting inside that capsule, you don't see electrons embedding themselves in insulation. You don't see charge building up inside materials. You don't see probabilities attached to solar activity. What you experience is a system that either behaves the way it should or doesn't, and the difference between those two outcomes can depend on effects that never make it into the visual narrative of the mission. Effects that accumulate slowly below the threshold of attention until they become relevant at exactly the moment when everything else is already demanding precision. There's a moment in almost every technical discussion about this mission where someone reaches for a familiar comfort, and it sounds something like this. We've done this before. We went to the moon in the 1960s. We brought people back safely. And if that was possible then, with far less advanced technology, surely it should be even more reliable now. And I understand the instinct behind that, because it feels like a logical progression. More knowledge, better materials, more powerful computers, all pointing toward reduced risk, But if you stay with that thought a little longer, it starts to unravel in a way that's not obvious at first. Because what you're really doing when you make that comparison is collapsing two very different systems into a single narrative. And physics doesn't let you do that without consequences. Apollo and Artemis are not the same problem with better tools. They are different problems with different structures. And one of the most important differences is not in what has been added, but in how those additions interact with each other. Apollo's systems, by modern standards, were remarkably simple, not because the engineers lacked sophistication, but because the constraints of the time forced them into designs with fewer layers, fewer interdependencies, fewer pathways through which a small deviation could propagate, and there is a kind of robustness in that simplicity that doesn't get enough credit. A system that does fewer things can fail in fewer ways. And when it does fail, the pathways are often easier to trace. Modern avionics are a different kind of achievement entirely. They are precise, adaptive, capable of handling complex guidance tasks that would have been impossible decades ago. And that capability is exactly what allows something like skip reentry to exist in a controlled form, but it comes with a cost that is less visible, which is that the system is no longer a collection of mostly independent parts. It is a tightly coupled network, sensors feeding into algorithms, algorithms driving actuators, actuators altering the environment, the sensors are measuring, all of it happening continuously and at high speed. I remember once trying to model a system that looked straightforward on paper, a set of variables with clear relationships, and everything behaved nicely until I connected two parts of the model that I had originally treated as separate, and suddenly the behavior became much harder to predict, not because anything was wrong, but because the interactions created feedback loops that weren't obvious when you looked at each component in isolation. And that's the kind of thing you start to think about when you hear that each subsystem on this spacecraft has been individually tested and certified. Because certification, in the engineering sense, is not a statement that nothing unexpected will happen. It's a statement that under a defined set of conditions, the system behaved within acceptable limits, and that's a very important distinction. It means you have bounded the risk for that subsystem, but it does not mean you have fully characterized what happens when that subsystem interacts with others under conditions that were not simultaneously present during testing. So now take a step back and look at what is actually being carried into the reentry phase. You have a heat shield whose behavior diverged from model predictions on its last flight. You have avionics that have been exposed to an elevated electron environment for an extended period. You have a guidance system that must continuously adjust trajectory during a two-phase atmospheric entry. And you have a communication blackout that removes any possibility of external intervention at the most critical moment. And each of these elements, on its own, has been evaluated and deemed acceptable. But they are not acting on their own. They are acting together. And this is where the idea of stacked uncertainties becomes more than just a phrase, because uncertainties don't simply add up in a linear way. They can interact, amplify, cancel, or transform each other. And the result is a system whose behavior cannot always be predicted by summing the behavior of its parts, especially when the environment itself is nonlinear. As the atmosphere is at hypersonic speeds, there's a term engineers use for this sometimes quietly because it doesn't sound reassuring. They call it unmodeled coupling. And what it means is that even if you have identified all the known variables, there may still be interactions between them that were not captured in your models. Not because of negligence, but because modeling every possible interaction in a sufficiently complex system is not something you can fully do. You approximate, you prioritize, You focus on what seems most likely to matter. And most of the time, that works. Most of the time, the system behaves within the envelope you've defined. But every now and then, you enter a regime where the combination of conditions is just different enough that the approximations are being asked to carry more weight than they were designed for, and that's not a failure of engineering. It's a fundamental limit of how we deal with complex systems. If you're sitting where I am, looking at this, not as a headline, but as a physical process, you start to see that the real question is not whether each piece of the system is safe, but whether the system as a whole has ever experienced this exact combination of conditions before. And in this case, the honest answer is no, because it couldn't have. This is the first crewed flight of this configuration, under these specific environmental conditions, with this particular sequence of events. And that doesn't mean something will go wrong, but it does mean that the confidence we have is built on a foundation that includes both what we know and what we have not yet observed. And the boundary between those two is exactly where the most interesting and sometimes uncomfortable physics tends to live. Not in the well-understood center of the model, but at its edges, where reality has a habit of reminding you that it always contains a little more than you accounted for. There is a region in space that doesn't look like anything when you try to imagine it. No visible boundary, no glowing gate, no line you can point to and say this is where things become critical. And yet, from a physics standpoint, it is one of the most unforgiving places in the entire mission. A narrow range of angles and velocities called the entry corridor, and everything the spacecraft has done up to this point, every correction, every burn, every quiet checklist after the lunar flyby has been shaping one thing only: whether the capsule arrives at that corridor in exactly the right way. Too steep, and the atmosphere does not forgive you. It doesn't gradually slow you down. It hits you. The forces rise faster than the structure is designed to tolerate. The heating intensifies beyond what the thermal protection system was built to absorb. And the difference between a survivable trajectory and a destructive one is measured not in kilometers, but in fractions of a degree, which is a strange thing to accept, that something so large, so energetics, can hinge on something so small. But that's what happens when velocity and atmosphere meet at this scale. Too shallow, and the problem reverses itself in a way that is just as unforgiving. The capsule does not penetrate deeply enough to shed the energy it carries. It skims, it lifts, and if the geometry is wrong, it can leave the atmosphere without slowing down enough. And then you are no longer on a path that leads cleanly to Earth's surface. You are on a path that extends uncertainty rather than resolving it. And by the time you realize which side of that boundary you are on, the opportunity to correct it has already passed. I once tried to balance a long object on a narrow edge, just to see how sensitive it was to small changes in angle. And what struck me wasn't that it fell, that was expected, but how little it took to push it from one outcome to another. How something that felt stable for a moment could tip with the slightest shift. And that memory comes back to me every time I think about this corridor. Because what looks like a broad return to Earth from a distance is, in reality, a very tight constraint that has been approached step by step over the course of days. By the time the spacecraft reaches the point where it is effectively committed, there are no more meaningful adjustments left to make. The trajectory is set. The vehicle is configured, and what follows is not decision-making in the usual sense, but execution. The systems doing what they were designed to do under conditions that are no longer negotiable, and inside mission control. The atmosphere reflects that shift. Not dramatics, not tense in the way people imagine tension, but focused, procedural, a kind of quiet that comes from knowing that everything that could be done has already been done. Then the atmosphere starts to take hold, not all at once, but progressively. The upper layers first, thin enough that you wouldn't notice them at ordinary speeds. But at this velocity, they matter immediately. The air compresses, the temperature rises, the plasma sheath begins to form, and from the outside, if you could see it, it would look like a streak of light, a brief artificial meteor cutting across the sky. But inside, what you feel is the onset of deceleration. The forces building, the environment changing in ways that are sensed more through the body than through direct observation. And then, just as all of this is reaching its most demanding phase, the connection disappears. Not gradually, not with warning, but cleanly. The radio signals no longer make it through the ionized layer surrounding the vehicle. The telemetry drops out, and the spacecraft becomes, for those few minutes, completely unreachable. Not metaphorically, but physically, the information cannot escape, and the control that existed a moment ago is replaced by a kind of enforced patience. I've always found it interesting that in a system as advanced as this, with all its sensors and computers and communication links, there is still a phase where the most accurate description of what is happening from the outside is simply that we don't know, not because we lack intelligence or preparation, but because the environment itself blocks our ability to observe, and that forces a different kind of trust, not in the sense that nothing can go wrong, but in the sense that whatever does happen will unfold without intervention. When the signal returns, it doesn't come back with a narrative. It comes back as data. Numbers, confirmation, parachutes deployed, descent stable. And only then does the abstract tension resolve into something concrete. The capsule descending through the lower atmosphere, the ocean rising to meet it, recovery teams moving in, and the 4 people inside transitioning from a system under extreme conditions to one that is once again part of the world they left. But the story doesn't end at splashdown, at least not in the way that matters most for what comes next. Because what the engineers will be looking at in the hours and days after is not the fact that the mission completed, but how it completed. Whether the heat shield behaved according to the updated models or introduced new deviations, whether the guidance system operated within its predicted envelope, whether the environment the spacecraft passed through left signatures in the data that need to be understood before another crew is sent along a similar path. There is a tendency to think of a successful mission as proof that everything was understood beforehand. But that's not how this kind of work actually proceeds. What you get instead is a refinement, a narrowing of uncertainty, a comparison between what you thought would happen and what did happen. And the gap between those two is where the next set of decisions will be made if you step back far enough beyond the details of this specific vehicle and this specific flight. What you see is a pattern that repeats across every attempt to push a little further than before. You build a model, you test it, you adjust it, and then at some point you have to decide that the remaining uncertainty is small enough that you are willing to proceed, knowing that the final confirmation will only come from the event itself. And that's the part that stays with me. Not the spectacle of the launch or the images of the moon, but this quiet, almost understated reality that at the center of all this precision, all this engineering, there is still a moment where the outcome is determined by how closely our description of the world matches the world itself. And the only way to find out is to let the two meet